In the third item on the first exam, you're going to find that you're asked to find the reaction at C and the tension in the cable, noting that there is only one cable, wraps around at D and is attached to the beam at A and points A and B. I have also already taken a look at what the right triangles are here that represent the angle of inclination of the cable segment. On the top, turns out to be a 5, 12, 13 triangle, and at the lower level, that's a 3, 4, and 5 right triangle. So rather than try to determine what the angles are and then put those use those later on, that will introduce numerical error. I'm just going to keep them just as is. If we want to find the tension in the cable, we're going to have to cut through the cable, and there's just this nice straightforward free body diagram here. Pull the pin at C, cut the two cables, and away we go. So here's point D, where we're going to ignore the friction of the diameter of the pulley, so that means the cable will head along in its line of action right towards D. And since there's only one cable, that's going to be a value T. And then here at this attachment point at B, we'll have the same thing. We have the same value of the magnitude of the cable. Does have a different line of action there. We've got the applied force of 120 newtons here at between A and B, and then we've got the two reactions at C. And I'm going to guess that CX has to push to the left because this beam with this load wants to try to dig into the wall, so the wall pushes back. And I'm also going to guess that CY, if I were to pull this pin, nothing else, that this thing would want to rotate up. In other words, there's a hold down reaction here. Just a guess. If I'm wrong, I'll just get a minus sign later on in my equations that tell me it needs to be the opposite direction. CX I can find by cleverly summing moments about point D, because it'll get rid of both cable forces, which I don't know, and it get rid of CY, which I also don't know. So it's a very clever way to go about doing this. We'll take clockwise as positive. When we sum moments about point D, we'll get a negative 120 times its perpendicular distance from its line of action over to D, so that's 280 millimeters, so there's a newton, there's a millimeter, and then plus, and then CX has a moment arm of 150 millimeters times CX. Set that equal to 0, solve. We'll have a positive value for CX, which means that I guessed correctly about the direction, which is shown to the left, and my number will be exactly 224 newtons for that value. Right? So I don't put the point there to indicate that that is an exact value. I can find T in a similar kind of way by being clever and summing moments about point C. It gets rid of CX and CY. There, I could have played around with sum of forces in the X, but then if I'd made a mistake with CX, then it would propagate on through. So why allow that to happen? So we'll have sum of moments about point C. Let's do the applied force first. It'll be again 120 times 280, and that'll be negative. And then we got to make sure that we get the Y components of T, and we don't care about the X components of each T because they'll pass through the point of interest. This first one, that's going to be this 5, 12, 13 relationship. So that's 5 over 13 times T, just to get the force. And then the moment arm is this whole length. That's 360. And then likewise for this other one, we want, again, the vertical part. So that's 3/5 of T. Its moment arm is 200. Set it equal to 0. We'll get a positive value for T, and it's going to equal 130 newtons. Notice no direction because it's the tension in the cable, and depending on what portion of the cable and which end of it that we look at would dictate whether that would be upwards to the right or downwards to the left. In other words, there's just the direction is wherever the cable segment is at and its in tension. And then for CY, you'd like to be able to find some place where CX, T, and T all intersect. there really isn't. So we're left with having to use intermediate results. Why not just sum forces in the y to get our cy value? And because we're going to have to reuse values anyways. Take upwards as positive, and we get then 5/13 of t plus then 3/5 of t, which we know to be 130, minus the 120 minus cy, set it equal to 0, and we'll get a positive value. When you do all this, you'll have 128 out of all that. And minus the 120 will give you a net of 8. Take it to the other side and get rid of any minus signs if you have any, and we'll get 8 newtons. A positive value for cy, meaning we guessed correct on the direction there. And so for a then final answer, we will have then that Cx equals 224 newtons acting to the left, Cy equaling 8 newtons acting down, and then T equals 130 newtons. Now, I had actually wanted you to take the next step here and find the resultant of Cx and Cy and its angle, express that in polar form. Many of you, it looked like, were running out of time on the test, so I was happy that this is how you've presented the results of your work, and if you didn't take that next step, I didn't consider that to be a less quality answer in this particular situation, and I was plenty happy to see that you got to this point in the exam, and away we shall go.